Okay, in this lesson, we're going to talk about vector-valued functions. We're going to take what we have learned about vectors, what we've reviewed from our pre-calculus and physics knowledge of vectors, and throw in some derivatives, a new form, linear combination form, and see what we can do with those. So first off, let's look at this linear combination form. So it says any vector v with components a and b can be written as a linear combination of the two standard unit vectors. Okay, so we talked about unit vectors being a vector with a length or a magnitude of 1. So there are two special unit vectors. There is the horizontal I unit vector that just goes out from the origin to 1, 0 if it's in the standard form, and the vertical unit vector j, which is the 0, 1 component vector. So if we have a linear combination form of AI plus BJ, then we can show that this is the same thing as our component form AB. If we take that coefficient of I and we replace our vector I with our component form 1, 0, and we replace our vector j with its component form 0, 1, and then we just distribute our a and our b. Okay, so a times 1, doing the scalar multiplication, is a times 0 is 0, b times 0 and b times 1 gives us the vector 0, comma b. Okay, so when we add those two vectors, we want to add our horizontal components. A plus 0 gives us a, and 0 plus b gives us b. So we can write any vector in component form ab in our linear combination form, ai plus b times the vector j. Okay, and again, I is this horizontal vector with a unit of 1, and j is this vertical vector with a unit of 1. Okay, so it's kind of the building blocks of any vector we can use in this linear combination form. So vector v is a linear combination of vectors I and j. The scalar a is the horizontal component of v, and the scalar b is the vertical component of v. Okay, so notice we've got this nice visual here. We've got some coefficient a times our horizontal vectors plus, using the head to tail method, some coefficient b times our vertical vector j, which gives us our resulting vector v, and we just showed how that's the same thing as component form AB. All right, so in example 1, it says let p equal -1, 5 and q equal 3, 2. It says write the vector pq as a linear combination of I and j. Okay, so I'm going to name this vector pq vector v, just for simplicity's sake. And let's see, vector v, if we want to put it in component form, let's try that again. Then we want to take our, if we're going from p to q, we've got our x1, y1, x2, y2. Then I want to take x2 minus x1. So 3 minus a -1, and y2 minus y1. So 3 minus -1 is 4. 2 minus 5 is a -3. So in component form, vector v is 4, -3, but we want to write it in linear combination form. Okay, so we have our a value here, our b value here. So we just stick those in front of our I and our j vectors. So horizontal component 4 times vector I plus our vertical component -3. We can actually just make that -3 times our vector j. All right, and there we've got our linear combination form of our vector. Okay, so moving on to vector valued functions. Says a particle moves through the plane on a time interval I with coordinates of the particle as functions defined by I. We've got our two components, our horizontal component x, which will represent as f of t, and our vertical component y, which will represent as g of t. Says the points x, y equal f of t comma g of t, where t is an element of our interval. All of those points together make up the curve in the plane that is the particle's path. We got a nice visual here of our vector valued function. Notice how we've got this curve. We've got a parametric curve. We've got these points that have time descriptors on it. And notice how we've got these vectors that are kind of in center position moving out to each of those points there. So thinking about each of the points on our function can be created with a vector, okay, at a given t value on our interval. So the vector r of t we'll use to name vector OP, where O comes from our origin. Okay, so just think of some vector with the tail at the origin going out to some point P, where the head is. We can say that's the same thing as vector f of t, g of t, in linear combination form. So this is component form. And here we've got linear combination form. Okay, from the origin to the particle's position at time t is the position vector. Okay, so again, going back to application of, we've got some position vector of a particle or of some object, and we can write that as a vector valued function. The functions f and g are the component functions of the position vector. The particle's path is the curve traced by r during or over the time interval I. So let's look at an example. Okay, example 2 says graph the vector function r of t, where t is greater than 0. Okay, notice we've got our horizontal component here next to our I, and our vertical component here next to our j. So we want to do is we want to graph this, and our interval is going to be for all time values that are positive. So if we want to graph it, a good way to start a graph is with a table. So let's start there. Okay, thinking about this like a parametric, we're going to need not just an xy table, but a txy table. Okay, we've got our time component. We have a separate x function and a separate y function. Okay, even though 0 is not included, let's start there as kind of a starting point. And then since our inputs for time are both trig functions, how about let's pick something that is reasonable, so we don't hurt ourselves with a whole bunch of decimals. Let's go by pi over 2s. I think if we do a full revolution, that'll be enough. Okay, from 0 to 2 pi. Okay, so we've got our time components. Now let's plug those in and find our horizontal and our vertical components. All right, thinking about our unit circle. just sketch our unit circle here for reference. Okay, so we plug in x. We plug in our first t value into x, 0. So the cosine of 0, so 0 degrees or 0 radians. Cosine is our x component, so that's a 1. 3 times 1 gives us 3. For our vertical component, we're going to plug it into our b. Again, think about this as this is like your a, I plus b times vector j. Okay, so the sine of 0 is 0. So 4 times 0 is 0, but then we take away 1 from 0 and we get a negative 1. Okay, again, not necessarily a point since it's not included in our interval, but it's a good starting place. Maybe we can do maybe an open circle there at 3, negative 1. Okay, so at 3, negative 1, open circle, that's at t equals 0. Okay, and then going back to our table, let's go ahead and fill in the rest of our table, and then we'll plot these points. Okay, so plugging in pi over 2, cosine of pi over 2 is 0, 3 times 0 is 0. Sine of pi over 2 is 1, times 4 is 4, take away 1 is 3. Cosine of pi is negative 1, times 3 is negative 3. Sine of pi is 0, times 4 is 0, minus 1. Cosine of 3 pi over 2 is negative 1. Negative 1 times 3. Is that right? Did I do that right? Nope, definitely didn't do that right. Anybody else catch that? This guy should be 0, negative 1. Pattern wasn't holding up. Okay, 3 pi over 2, cosine of 3 pi over 2 is 0. 0 times 3 is 0. Plugging in 3 pi over 2 to sine, we get our negative 1. Negative 1 times 4 is negative 4. Minus 1 is negative 5. And then we'll end with 2 pi, coming back around full circle. We're going to get the same values as we did for 0. Coterminal angles. Okay, so let's plot these points. These 1, 2, 3, 4 points here. We've got 0, 3. Okay, that's when time equals pi over 2. We've got negative 3, negative 1. That's when our time component is pi. And when time is 3 pi over 2, we have 0, negative 5. And at 2 pi, we're back over to 3, negative 1, so we're just going to fill that circle in right there. Okay, so we get this, knowing that these are trig, sine, and cosine functions, they're going to be curves and not straight line segments. But we're going to get this elliptical shape here. Not the best rendering, but you get the idea. We've got this circular elliptical graph here. Okay, from our vector valued function. All right, so we can find the limit of a vector function if we let r of t equal r f of t I plus g of t I. If the limit of our f of t, okay, our horizontal component, as t approaches some value c equals some limit L1, and same thing for our vertical component, it equals some limit value, then the limit of r of t, our vector valued function, as t approaches some value c, is defined by our limit of r of t equals the limit times limit of our horizontal component times our I vector plus the limit of our vertical component times the j vector. Okay, so let's look at a couple of quick examples finding the limit of a vector function. In example 3, it says let r of t equal cosine of ti plus sine of tj. We want to find the limit of r of t as t approaches pi over 4. Okay, so we want to find the limit of r of t. This is vector r of t as t approaches pi over 4. Okay, so with limits, we want to try direct substitution first. We've got two trig functions, so we can plug in our what t is approaching. So we're going to have cosine of pi over 4 I plus the sine of pi over 4 j. Okay, cosine of pi over 4, that is root 2 over 2. Sine of pi over 4 is the same. So we get our limit to be our vector root 2 over 2i plus root 2 over 2j. Okay, notice that in our definition for a limit of a vector function, we get a vector out. All right, another example, example 4, says let r of t equal t squared I plus natural log of t minus 3j. Find the limit of r of t as t approaches 0. All right, so we want to start this one off the same way. We want to find the limit of r of t. Oh my goodness. As t approaches 0. Okay, so we want to find the limit of each of these components separately. As t approaches 0, again, we're going to start with direct substitution. If we have to go to other methods for calculating the limit, we could. But I think direct substitution is going to be fine for now. All right, so we have 0 squared I plus the natural log of 0 minus 3 times vector j. Okay, so 0 squared is 0, so we get 0 I, and 0 minus 3 is negative 3, and that's not okay. Okay, we can't take the natural log of a negative number. It's not possible. So this limit here is undefined, or does not exist, so therefore the limit of our function, r of t, our vector valued function, also does not exist. Okay, so when we run into a limit with either of our components that does not exist, then the limit of our whole vector value function also does not exist. All right, next up, derivative of a vector function. Nothing too fancy here. We're going to be applying what we know about derivatives to the components of a vector valued function. It says let r of t equal f of ti plus g of tj with components made up of the differentiable functions f of t and g of t. It says in the derivative of r of t is dr dt, or if we use our prime notation, r prime of t. And what we're doing is we are just taking the derivative of the horizontal component as a function of t, derivative of the vertical component separately as a function of t. Okay, again, nothing too extreme, nothing, no new procedures or tasks or anything. We're just kind of finding two separate derivatives within one of these vector valued functions. So let's try one. Example 5. Similar looking function. It says let r of t equal cosine of ti plus sine of tj. We want to find the derivative of r. So derivative of r of t. So we want to take the Derivative of our horizontal component, derivative of cosine, is the opposite of sine. And the derivative of sine is cosine. Oops. And that's it. It's the derivative of our function r. Again, just taking the derivative of each of the components separately. Okay, likewise, for the integral of a vector function, same deal. If we want to find the integral over some interval from a to b, then we're going to do it to each component individually, f of t and g of t. All right, so looking at example 6, says evaluate the integral from 0 to pi of cosine of ti plus 2tj dt. So we're going to find the integral from 0 to pi of our horizontal component dt, and we're going to multiply that by I. And we're going to add that to the integral from 0 to pi of our vertical component, dt, times vector j. I'm actually going to slide this over a little bit for space sake. Okay, so again, no new procedures, no new tricks or anything. We're just taking the integral of each individual component, the a component, the b component, or x and y, horizontal, vertical, however you want to think about it. So many different representations. All right, so one at a time. Integral of cosine of t is sine of t. So we're going to go sine of t. We want to integrate that from 0 to pi. And that's going to be times I. And our second piece here, integral of 2t is just t squared. We want to integrate that from 0 to pi. That's going to be our b value times vector j. Okay, so sine from pi to 0, or from 0 to pi, is going to be sine of pi minus sine of 0. And our b value, plug in pi, we get pi squared minus 0 squared for our j vector. Okay, let's see. Sine of pi is 0, minus sine of 0 is also 0. So we have 0 I component. Pi squared minus 0 is just pi squared, so we have pi squared times vector j. Okay, so 0I plus pi squared j is our solution for that. Okay, two more examples. In example 7, says find an equation for r of t and v of t if a of t equals blah, 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 via v naught and r naught they give it to us. So in this problem, we've got to understand that they're not just giving us these randomly named vectors. This guy here is our position vector. This is our velocity vector. And this is our acceleration vector. Okay, so keeping that in mind, if we know that, let's start over here with our what they give us, our acceleration vector of t. Okay, so they give us 2t I minus 5j. And let's see, they want us to find an equation for r of t and v of t. Okay, so if we know our acceleration vector, let's go ahead and get our velocity vector next. Comes next in line. Okay, so let's see. If we integrate our acceleration vector, then we get t squared I minus 5t times our vector j plus some constant. Okay, so notice in the last example we had a definite integral, so we didn't need to worry about our constant c. Here we don't, so let's consider some extra part to this. And to find what this is, they tell us that our v naught is 3i minus 2j. So we can use that to find out what this extra constant is out here. Okay, and for a vector function, it could have parts both in A and in B. Okay, so let's take that 3i minus 2j, and knowing that that's equal to v naught, let's set it equal to what would happen if we plugged in 0 into our t's. Okay, in our velocity equation. So we get 0 squared. That's just 0. Minus 5 times 0. That's just 0 again. Plus c. So we get our c value is this almost like a y-intercept for our velocity function. 3i minus 2j. Okay, so with that, we need to add in these extra components to our a and our b values up here. Okay, so our velocity as a function of t. Okay, for our a component, we've still got this t squared, but now we've also has this 3i that we have to add in there. Okay, we can put those in parentheses and just have a single I vector. And for our vertical component, we have a negative 5t, but then we also just found we have a negative 2. So we combine those together to get our vertical component. Okay, so this gives us our vertical vector as a function of t. Okay, but they also asked for the position vector. So let's take that vertical vector, or that velocity vector, excuse me, and let's integrate to find our position vector, our r of t. Ugh. Okay, so integrating our velocity vector, maybe, yeah, I'll just leave it. Parentheses, we get t cubed over 3 plus 3t. Plus a negative 5 halves t squared minus 2t. Okay, don't forget the plus c. And they give us in the problem, in addition to the v of 0, they give us the r of 0, which is I plus j. So let's use that to find our constant value. So if we say r naught is equal to I vector plus j vector, then let's take that I plus j and let's set it equal to what would happen if we plugged in 0 into our r of t function we just found. Okay, so we've got 0 cubed over 3. That's 0 plus 3 times 0. We've got 0 squared times whatever is still going to be 0. Minus 2 times 0 is still 0. So we're going to get our I plus j. Is our c value. That's what we want to add in. Okay, and again, think about those coefficients. We've got a 1i and a 1j. So we want to add those in to our a and our b values up here for our position vector. Okay, so our r of t we want to take our let's see, let's call that 1/3 t cubed plus 3t from up here, and then we're going to add in this 1i that we have. So plus 1 in parentheses. All of that is our a value. And let's see, do I have space? Yeah. And for our b value, let's take our negative 5/2 t squared minus 2t. And we also had a 1j over here, so let's add that in. And we're done. That's our position vector. Okay, again, being given our acceleration function as a vector value function, integrating it to find our velocity function. Okay, our unique velocity function, since we're given a specific v naught here, and then integrating that to find our position function. Again, our unique position function being given r naught. All right, last example. Example 8 says the vector r of t equals 2t cubed minus 3t squared I plus t cubed minus 12tj gives the position of a particle at time t. All right, part A says write an equation for the line tangent to the path of the particle at the point where t equals -1. All right, I'm going to have to write small on this one. Got some steps to do. All right, so this is a typical kind of example that we've done ever since we learned about derivatives back in AB, is finding an equation for a line tangent to a given function. Okay, now the only difference is now we have a vector value function. Yeah. Ooh, yours does say 1. Change it to -1. Not everything got fixed. Okay, did everybody see that? So on your example. Did yours say example 8 or example 9? Example 8, okay. On your example 8, make sure that you make that t equals -1. Great, all right, so for an equation for the line, again, linear equation, the two things we need are a slope and a point. Okay, so let's start by looking for our slope. All right, to find our slope, we need to find our derivative function. Okay, so derivative of that r of t function, we're going to get 6t squared minus 6t. for our a value, and for our b value, we're going to get 3t squared minus 12. Again, just using the power rule, taking simple derivatives. Okay, but again, so this will give you the slope at any point, but we want specifically at time of -1. So plugging in that -1 to our function. See, -1 squared is 1 times 6. This is going to be plus 6 is 12. Plugging in -1 squared is just going to be 1. 3 minus 12 is going to be minus 9. J. Okay, so we have our derivative function, our r prime, but it's as a vector. So we don't want to plug in a vector as our slope in a linear equation. So we're going to take that. We're going to find our dy dx. And we're just going to take that b value and that a value. Okay, b value being the rise, the dy. The a value being the run, the dx. And since these both are divisible by 3, let's simplify. Okay, so our slope for our tangent line at time -1 is -3/4. So we have a direction. Again, this is our slope. But we just don't have a position yet. So now we got to find our position. So all this was for our slope. So now let's find our position. Let's find our point. Okay, so we got to go to our position functions. That's r. So we want to find r of 1. So plugging in 1 into our function. Ooh, -1, thank you. Good, so plugging in -1. A -1 cubed is negative, so we get a -2. -1 squared is a +1 minus 3, so we get a -5 for our a component. Plug it into our b component. -1 minus a negative, so that's plus 12, so that gives us a +11 for our b component. Okay, and we just want those components. Again, just like for slope, we just used the a component, the b component. We're going to steal our a component for our horizontal, b component for our vertical, our x and our y. And so we get our point. Okay, so we have our position. We already have our slope. So again, thinking point slope form. Let's plug it in. So we're going to have y minus our y1, 11, equals our slope, times x minus our x component, and we're done. So this is the equation of the line tangent to our position function at time -1. All right, 2 more parts. Find the coordinates of each point where the horizontal component of the velocity is 0. Horizontal component of the velocity, okay, that's important. Okay, and we want to find the coordinates of each point. Okay, so we're looking for just a x, y. Okay, maybe more than one. All right, so we're our horizontal component of velocity. So we want to find our dx dt, which we already found up above. That's our, let's see, our a component up here of r prime. Okay, and in order to find where our velocity is 0, we want to set that equal to 0. Okay, doing a little bit of factoring, we can factor out a 6t. So we get t minus 1. Okay, set each of those equal to 0. We're going to get t is either equal to 0 or 1. Okay, so we found the moments in time where our horizontal component of the velocity was 0, but now we want to find the coordinates of each point. All right, so we want to find r of 0, and we want to find r of 1. What's that?
Would it be where the derivative of y equals 0 to get the horizontal?
Well, so because we're just looking at the horizontal component, so we're just looking at this piece right here. So which doesn't necessarily mean that it is a flat line tangent. All right, so plugging these in back up into our position vector, we get 0 minus 0, that's 0i, and 0 minus 0 for our b, 0j, so we get the point 0, 0. And plugging in 1, we're going to get a negative 1i minus 11j, which gives us the point negative 1, negative 11. Okay, so those are our 2 points where our horizontal component of our velocity vector, or of the velocity, is 0. Last one, part C, find the acceleration vector at time t equals 2. Okay, so knowing that our prime of t, which is our velocity, which we found above to be 6t squared minus 6t, I plus 3t squared minus 12j. Okay, to find acceleration, we want to take the derivative of velocity. So we want to find our double prime of t, which is v prime of t, which is going to give us our acceleration. Okay, so derivative of each of these, power rule, we get 12t minus 6. Power rule, we get 6t minus 0. Okay, so we get our acceleration vector, but we want it specifically at this time. So let's find, lastly, the acceleration at 2 seconds or hours or minutes, whatever our units are. And plugging in 2, we get 24 minus 6. Plugging in 2, we get 12 for our b value. And so we get the acceleration vector of 18i plus 12j. Okay, so we looked at using our basics of derivatives with our vector value functions to analyze path of a particle, derivatives and integrals. We looked at finding the limit of a vector value function and graphing a vector value function, okay, from linear combination form.